we're going to continue talking about structures today. In particular, I guess we're still talking about trusses. And today I'm going to show you another method of analyzing a truss to figure out how much force is in some of the members of the truss. All right, and in particular, this method that I'm going to show you today is good for finding the amount of force that exists in a member that's at the middle of a fairly long truss. All right, and so let's get started with this. I've got here a truss that is made of popsicle sticks, obviously, but this truss, because all the things have about the same length, it's fairly simple. These are all basically equilateral triangles. But let's say that I had this truss and I wanted to set it up and support it at its ends. All right, I've got some supports here. They're actually Tolkien books, but you can use whatever you want. We got Tolkien books here as our supports, and set that up. And let's say we had it supported at its ends like this, and we wanted to load it, let's say right above this joint right here. And that was how we had our truss set up. So we're going to put a downward load there, support it at its ends, and let's say that you wanted to figure out how much force was in these middle members right here. Either that top one right there, or this one that's diagonal right there, or maybe the one that's along the bottom. In order to do that with the method of joints that we learned last time, you actually have to start at one end and work your way all the way over and figure out what those forces are in those members. Well, we want an easier way to do that, and so this is what I propose. What if we actually took the truss apart? This is a very common thing for us to do if we're trying to figure out how much force exists inside of a structure. You actually make a cut in the structure and figure out, all right, what is the amount of force that happens in this particular location. When we do this, what we need to do is actually make a cut all the way through the truss. We'll start top to bottom, and we need to cut through no more than 3 members. All right, so you start here and cut through those members, and by doing that, what we basically do is reduce this truss into 2 separate structures. We basically would eliminate these members right here, and that leaves us with these 2 structures. All right, that won't hold itself up now. But what we can do is replace those members, what used to be members right there, with the forces that those members would have exerted on the pins that they were connected to. And so that's the method that we're going to do. This is called the method of sections. The reason it's called method of sections is that you're actually cutting this truss into 2 separate sections. And by doing that, you can analyze it and figure out what the forces are in those missing members without having to solve for everything in the rest of the truss.
So here's the truss that I showed you just a couple seconds ago, and if you'll remember on this truss, remember we had it supported at the ends. So here we'd have a support there and a support here. Alright, I'm going to go ahead and name those. This is RAY, I'll call that, and this over here is RFY. Alright, just to kind of indicate here that we always have to have something that keeps it from moving in the X direction. Even if this is the only force we have in the X direction, we still need to show it there because something keeps it from just, sliding off with basically 0 force. So we'll go ahead and put that in there, RAX. Alright, and we also said that it was going to be loaded above one of these joints right here. I'll show it being loaded right here. All right, and let's just assume some value for that. I'm going to say that this is 40 pounds. All right, so that's the situation we had. It's being loaded on joint C, and it's being supported at joints A and F. All right, and just to remind ourselves, the members that we are trying to find the force in, those members are CD, DH, and HG. Those members right there are the ones that we're trying to locate the amount of force, or trying to figure out the amount of force in those members. All right. Now that we have the reactions, we can go ahead with the rest of this analysis. And as I mentioned before, when you want to do this method of sections, what you have to do is you have to make a cut through the truss. And when you do that, basically you pick a point in the truss where you can cut through the member or members that you are trying to figure out the force in. And so here I'm looking at this. If we make a cut through this truss that goes down right through here, it cuts all the way through those members, and what we're going to do is eliminate those members and draw free body diagrams of the two sections of the truss that are left over. Alright, so now that we've made that cut, I'm going to start with this section that's over here on the left. Alright, and so drawing that free body diagram, we have something that looks approximately like this. Let's see, try to make this look pretty close to being the way the other one is. Alright. Alright, so there's the that section of the truss, and we know that this is a 25-pound force that acts right here. Alright, we knew that this was a 40-pound force that acts up here. And if we look at it, we did have the 0-pound force that happened at A, but if we look at it, that's really the only forces we already knew before. But the thing is, now that we made that cut through the truss right there, there's some other forces that we need to account for and put on this free body diagram. Alright, one of those forces is going to be this force up here in CD. And since all these are two force members, we already know the direction of that force in CD. So it goes right up here. This is, we'll just call it F, or we'll call it TCD. Remind ourselves that that's in tension. TCD. All right. And so then we look at other ones. We also have this force right here, and that we can call TDH. We also have a force that acts in this direction over here, and this is TGH. All right. Now, looking at this free body diagram, one of the first things we need to ask ourselves is this a concurrent force system or is this a non-concurrent force system? And you can see fairly quickly here that this is a non-concurrent force system. If you look at the lines of action of some of these forces, there's a line of action of the 40-pound force. Here's a line of action of the 25-pound force. We have this line of action for a TCD. We have another line of action that goes there. So all those lines of action right there, they don't all pass through the same point. And that being the case, we really can't treat this as a concurrent force system. That's the first major difference between this method and the method of joints, is that in this method, we're doing free body diagrams of non-concurrent force systems, and so that means we have to sum forces and moments in order to be able to solve for the things that we are trying to determine. All right, let me go ahead and finish this out. I'm going to call this the X direction. I'm going to call this the Y direction. And the only other thing that I'd really like to know on here are a couple of lengths. We want to know maybe that this is 5 inches here and another 5 inches there. We'd also want to know what direction this TDH went, and because everything is symmetric there, we have all these equilateral triangles, we know that that angle right there is 60 degrees. So I'll stick that in there, that that's 60 degrees. We also know up here this is 5 inches, and so I'll stick that in there as well. So there's a good free body diagram for that first piece. All right, let me kind of finish it out. One more thing here and put some labels on there. That's A, that's B, this is C, that's H right there, and this is I down here. Continuing on with our process of splitting this truss in two, we've done this one free body diagram over here There's actually another one we could draw for the right side of the truss, and so let me go ahead and do that one. Over there we have this basically a parallelogram with a diagonal in it, so we'll go ahead and draw that something like this. We got a joint there, a joint there. We have another joint here. Excuse me. We would have another joint about here. That comes down like this. That comes down like that. And then we'd have another joint basically over here. Okay, so this is the piece of the truss that's over there on the right. That's joint D. This is joint E. That's F. And this is G. Okay. And if we look at that, we actually have one external reaction that we can put on there. We know that that force right there is 15 pounds. But we have some other forces here due to these members, and we've already identified all these variables. We've already identified them over here on this other diagram, and so we need to be consistent with that other diagram when we draw them on this diagram. If we showed TCD pulling to the right on C, that must mean that it's pulling back to the left on joint D. All right, you imagine grabbing those two joints and pulling them closer together. That's basically what that member TCD, that's what we're assuming that does. All right, so we'll call that TCD. The other thing we need to do is we need to look at this member DH, and it acts downward in this direction. So that there would be TDH. And then we have another force that acts to the left right there that we call TGH. Okay. Notice with all these that I'm being consistent with what I had on the last free body diagram. If something pulls to the right on the left free body diagram, then it's going to pull to the left on this free body diagram over here on the right. All right. We'll use the same coordinate axes, X and Y here. I guess I'll stick them on there, something like this. All right, and then we'll make sure we get the rest of our stuff on here that we need. We know that's a 60-degree angle right there. We know that this is a 5-inch distance right here. All right, we know that there's this is 5 inches down here also. All right. And there we've got a couple of pretty decent free body diagrams for this thing. Now that we've got these things, the next step in the whole project is to try to determine which one we want to start with. We are trying to determine these three values, TCD, TDH, and TGH. We can use either diagram we want to, and as soon as we choose a diagram, we can write equilibrium equations. So the question we need to look at here is how do you choose? All right. You probably want to choose something that you can solve quickly for one of the variables. All right. And I'm going to show you here. It really actually doesn't matter a whole lot which one you choose first. And because of that, what we're going to do is we're going to choose this one over here on the left first. So we're going to take this free body diagram here on the left, and we're going to try to see if there's a variable that we can solve for immediately. If there's an equation we can use and solve for one of these variables immediately without having to solve for any of the other ones. In other words, we're trying to find something that gives us a one equation and one unknown type of a deal. And if we look at it, then what we've got is this vertical load of 25 here and a vertical load of 40 there, and TDH has a vertical component, but those are the only things we've got with vertical components. And because of that, we can take this and sum forces in the y direction. We'll take upward to be positive, and this gives us 25 pounds minus 40 pounds plus, we need just the vertical component of TDH to add into this thing. So we'll take TDH, and that's a 60-degree angle. We need the vertical component, and so that's actually the opposite from where that angle is measured, so that would end up being the sine of 60 degrees. All that's equal to 0. Okay, so rearranging this a little bit, this ends up being that TDH is equal to 40 minus 25 is 15 pounds divided by the sine of 60 degrees, and if you evaluate that, it ends up giving you 17.32 pounds. All right, so very painlessly we have gone through here. All we had to do is find reactions, and then when we found the reactions, do this one free body diagram, do one equation, and we get this value of 17.32 pounds. So we found the force in DH, but I tell you what, let's pretend that we hadn't. Let's go back here a step or two and actually pretend that none of this happened. All right. We're going to erase all that stuff. Tell you what, I'll keep the 17.32 just because we may need that later, but I'll keep it over here somewhere. But we're going to pretend that we don't have it, and instead we're going to sit here and we're going to solve this thing for something else. All right, we need to find one of these other variables, and if you think about it, is there another equation that we could write that eliminates all but one variable, just like we did in the last time around? And there is, actually. If you do a free body diagram of this body, which we've done, you can see that we've got these two forces, TDH and TGH, that go through this point H right here. And so that actually allows us to think about this and sum moments about point H. You can sum moments about any point on here that you want. And if you sum moments about point H, taking counterclockwise to be positive, you'll see here that the equation we end up with, this 25 tends to rotate it clockwise, so we have this 25 pounds or minus 25 pounds times its distance away from H, which would be 10 inches. Then we have this 40 pounds up here, all right, and that tends to rotate it counterclockwise, all right, and so that would be plus 40 pounds times 2.5 inches. All right, and then we look at the only other force we've got here that that would create a moment about H is TCD, and it looks to me like TCD creates a clockwise moment, so we'll take this as minus TCD. All right, and what we need to do there is figure out this perpendicular distance of TCD away from H, and so what we need to do there is we can actually kind of use the reverse Pythagorean theorem here, and I'll show you what I mean by that. That distance will just be the square root of the hypotenuse squared, which is 5 inches squared. Okay, 5 inches squared. All right, minus this one of these legs squared. So we have minus 2.5 inches squared. Okay, and that's all we've got there. We can set all that equal to 0. So rearranging this thing, we've got here TCD times this square root. If you actually evaluate this square root right here, that ends up giving you a value of 4.33 inches is equal to minus 25 pounds times 10 inches, which is minus 250 inch pounds. All right, plus 40 times 2.5 actually gives you 100 inch pounds. Okay, and so going from there, we can now solve, we can divide both sides by 4.33 inches, and we can figure out that TCD is equal to 34.64 pounds. All right. And so there, without having to know anything before we started that, we did one equation and we found the value of TCD. All right. So you can start seeing here, this is a really handy method because it doesn't mean that you have to solve the whole thing to get to a particular point in your truss. All right. So we've actually now found TDH and this value TCD. Actually, we need to correct that just a little bit. I missed that minus sign there. So this is actually a negative 34.64 pounds. All right, that's a value that's in compression there, basically up there at the top of that truss. All right. Again, let's do the same thing as we did last time. Let's assume that we haven't done these things yet. All right, and so I'm going to go here and again erase all this stuff that we just did. All right, get rid of all this and get rid of all that. All right, and I guess I'll hang on to this value also, this negative 34.64 pounds. We'll kind of keep this up here also because we found them, so we don't really necessarily want to get rid of them. But I want to show you that it doesn't really matter which one of these you do first. You can actually go to any one of them first. All right, and so the next thing we can do is move on to member GH. Now the thing with GH, I'll put that in up here. This is member GH. All right, so the thing is that it's a little harder to picture how to do that off of this free body diagram. So let's just go straight down to this free body diagram down here. This one over here. We'll go ahead and try to figure out if there's an equation we can write for this free body diagram that allows us to solve for TGH in one step. And you can see here that if we do a free body, or if we had some moments here about joint D, all right, some of those moments about joint D, TCD and TDH will not appear in that equation because they have lines of action that go through that joint. So we'll go ahead and start doing that. Summing forces for this free body diagram, I'll kind of put this like this so that we don't confuse it. We're going to sum forces for this free body diagram over here, sum moments about joint D. And we're going to take counterclockwise again as our positive direction. We've got that 15-pound force over there that does create that counterclockwise rotation about D. So that would be a plus 15 pounds multiplied by its perpendicular distance away from D, which is 7.5 inches. All right, and we're look around here. The only other force we've got that creates a moment about D would be TGH, and it looks to me like it tends to rotate it clockwise, and so we'll take this as a negative TGH. All right, multiplied by its perpendicular distance, and based on what we did last time, we'll remember that this height right here is 4.33 inches, or you could recalculate that if you wanted to. You could figure out what that height is. It's just a Pythagorean theorem type of thing. And all that's equal to 0. All right? So really, we've got a pretty simple task ahead of us here. Solving for this equation, we'll see that we've got 15 times 7.5 gives us 112.5. Okay, so here we'll say TGH is equal to 112.5 inch-pounds divided by this value of 4.33 inches. All right, and so evaluating that, we get a value here of 25.98 pounds. All right. So there's our value that we got for that TGH. Okay. We have now found all three of the values that we were hoping to get. So we've now found all the values we were looking for, the force in CD, DH, and GH. Let's look at one other thing though. I went ahead and drew both of these free body diagrams because I wanted you to see that either one of those free body diagrams you could do, and I wanted you to see the relationship between the two free body diagrams. The cool thing about this method though is that a lot of times you really only have to draw one. The last analysis we did this, found the force in GH based on this free body diagram over here. We could have actually done it fairly easily with this free body diagram over here, but it takes one little trick that I want to show you. Whenever you decide to sum moments on a free body diagram, you actually do not have to pick a point that is on the body like we did for these bodies here. You can actually pick a point that is off the body. All right. Looking at that, if you pick a point that's off of this body, you can actually pick a point that's over here somewhere. And actually, if you're going to name that point, that would be point D. All right. If you think about its relationship to our original diagram over there, if you take this free body diagram on the left and sum moments about joint D, you'll see there that that eliminates TCD and TDH out of that equation, and you end up with an equation that only has TGH in it. It makes that really easy to solve. So let's go ahead and stick that in here. Let's take a sum of moments about point D for this free body diagram, and doing that we'll find that we have this 25-pound load that creates a clockwise moment about D. That's minus 25 pounds times its perpendicular distance away from D, which would be 5 plus 5 plus 2.5. All right, so this looks like it'd be 12.5 inches away from that joint D. And then we have this 40-pound load that creates a counterclockwise moment about D. So I'll say this is plus 40 pounds times its perpendicular distance away from D, which is simply 5 inches. All right. And again, let's kind of isolate that so we don't let that interfere with our analysis over there. And then the only other force we've got here that creates a moment about joint D is TGH, and that's what we're looking for. All right, and it looks to me like if it goes in that direction, it's going to create a counterclockwise moment about D. So what that gives us here is a plus TGH times its perpendicular distance away from point D, which again is 4.33 inches. All right, and that's it. That's all the only forces we've got there. So we set all that equal to 0, and if we go ahead and solve that, we will again come out with that TGH is just equal to 25.98 pounds. All right, so here's TGH. This up here, this value actually here was TDH, and this one here was TCD, and that's the only forces we were actually looking for in that particular example. And I've shown you how you actually really only have to draw one free body diagram. Although drawing two of them lets you see the whole interaction. And you really can usually boil this down to where you only have to solve for one variable at a time. And so that's a really nice thing to be able to do.